Hi, I'm Gaurav Dabra. That's me on the top. Um, and good afternoon, everybody. Many thanks for joining. And everybody who is also on the remote. Um, Excited to be here and for the first time talking about the segment routing v6 technology. We have developed this technology for some time now, so very happy and excited to share what we have developed and take your opinions. As you can see, my co-authors, Comcast was supposed to join this talk, but due to last minute changes, they are not able to make it. This content has been reviewed by them, so we'll be covering the content, including the use cases for Comcast. All right, let's dive straight into it. Let me see this. Okay. As you can see, there's a big agenda. We'll be covering a lot of use cases. We'll be starting with the concept of segment routing. What is segment routing? Why we have developed it? We'll be touching into segment routing v6, why we have developed segment routing v6, and the most interesting part is the use cases, which impact how do we deploy the segment routing v6 in the network. So as you can see, there's a lot of use cases which I have listed over here. There are more of it. So obviously, if you have any questions, if you'd like to partner, please reach out to me after the talk, and we can discuss some more, and I can explain some more technically. So what is segment routing? Segment routing is source routing. We have developed segment routing for about 4 or 5 years. We started in late 2012. It's a source routing where the source can select a path over the network. And it's a topological path. If you have NFV nodes in the network, it can even select NFV nodes as part of the path from source to the destination. And on top of it, it also serves the application which has some SLA requirements like latency, bandwidth. We do not maintain any state in the network. And that's the beauty of it, because that way it can scale. It's a scalable. We have proven in the last 4 or 5 years that it can scale very well in the service provider networks, in DC, in WAN. And it also, on top of it, provides the automation. We have built a technology, TI-LFA. Everything is done automatically. The IGP does the backup path calculations. I'll be covering more into the details of that. And just the mantra of creating the technology, we have tried to simplify the deployment of it. We try to simplify the automation of it, and in the need of that, we also try to eliminate the unnecessary protocols which we don't need. We developed the TIF-LFA technology for about 3 or 4 years ago. It has been shipping in the products. It has been very widely deployed, and it's one of the most prevalent use cases which is out there. What happens is that once we have determined that a source wants to go from one point to another point, it uses an SR policy, and that SR policy is what is steering the traffic from the source to the destination. This technology has been deployed for the SP, for data center, and for WAN. So the use case is very prevalent. It's not constrained to one domain. So it enables more usefulness for the technology, the more significance of the technology, and I'll be going into the details of that. We started, as I said, about 2012, late 2012, 4 years ago, and we have developed a good, strong adoption in customer network with the scalability. We have done a lot of standardization. Segment routing team have published over 30 drafts, and everything which we do, not a single piece of technology is not standardized. Everything which we have written is in the IETF. You can go read it, and it's about 30 documents which we have published for segment routing MPLS. It's also a de facto SDN. When we started on segment routing, we thought about SDN and how the segment routing will impact SDN, whether it's programmability, the automation, the overall framework of it. We have developed it with SDN in mind. We have also automated everything, so you can have a centralized control or you can have a distributed control. It's completely up to you. And of course, we have a big commitment for our lead operators. So we have developed the technology with multi-vendor consensus, and we worked very hard to build that consensus over time. Now, I gave you a brief history about segment routing. Let's dive into the objectives of segment routing v6, why it's needed. So obviously, with the IoT services and 5G, we are seeing a drastic evolution on the edge. We are seeing, if you look at the data center, we are seeing a lot of microservices, clear migration towards microservices, container-based networking, and a drastic increase in the services where the appliance would be requiring an IPv6 or IP reachability. It's clear to us that the IPv6 will prevail and in the modern IP architecture. And the bigger space for the IPv6 is an obvious choice. So once you have laid down the IPv6 reachability, question now is that whether this will happen or not. Question is, how do we address this IPv6 support to serve the applications? And let me give you one example where we have segment routing v6 being used for 5G, where the 5G have requirements like scalability, it has service requirements, it has slicing, traffic engineering. And for all of that, one would say one obvious choice is to use RSVP, but we have seen some scaling issues with the RSVP. So what we are proposing, or segment routing v6 is going to happen. It's obvious to us that segment routing v6 will prevail, and it will deliver the same level of services which we have done for SR-MPLS, which is simplicity, FRR, traffic engineering, and couple everything together with SDN architecture. We also see that in order for some of these services, on top of the underlay, you have an overlay. The overlay is right now, you can have UDP, you can have VXLAN overlay. And the reason we are doing these two additional protocols is to signal the tenant ID. No, we do not need these protocols if they're not really required. We can encode this information in SR policy, which can be carried in the SR header. And what is a layer after overlay is NFV. There is a protocol, NSH, which has been designed, and that particular protocol is yet another protocol adding another layer of overlay complexity and maintaining the state in the fabric itself. We want scalability, we want the flexibility, and we want the simplicity. So we want to remove these protocols and try to encode all this information in segment routing v6. Obviously, if you're interested in learning more details about it, please contact me, and we can go and have more data to prove that this will happen. We have also built some proof of concepts, so we can show that to you also. Economics of free market evolves, and it tries to eliminate the redundancy, it tries to eliminate the inefficiency, and we believe that the layering of these protocols may not be the right approach in order to solve the problems of next generation IPv6 or IP network. We believe there is a possibility to eliminate some of these protocols and simplify the solution. So now I have talked about why we need it. Let's dive into it, how we will evolve and build this next generation IP network. So we are introducing a new concept of network as a computer. Now, 1 second, sorry. In order to do that, we have these IPv6 addresses which are available. We will not use all the IPv6 addresses. Most of the IPv6 addresses will be available in the classical way. We will only use some IPv6 address, 128-bit space which is available. We call it SID, or segment identifier. Now, if we split the segment identifier in the middle, where you have 64 bits available for the locator, you have 64 bits available for the function, then uh, then you have a possibility where you can encode more information in those 128 bits which are available in IPv6 address. However, I'm taking an example over here of 64 bits as network and 64 bits as function. They're no way constrained. You can do the way you want to. I'm just using this example so that I can showcase and try to walk through the different things which we have built with segment routing v6. Now let's say the first 64 bits is available, and those first 64 bits can be used as a network reachability. So how do you get from to a particular node? You can do that information using the first 64 bits. The rest of the 64 bits can be used as a function which is locally to that particular node. That, hey, once I receive the packet, it says, okay, this function belongs to me, and then I should be able to do something with it. Again, we are trying to keep a simplicity, and we are trying to, there is also a concept of arguments, but for the simplicity, I'm just trying to, talk about locator and function for now. Okay. So now, once we have this network instruction, we need to put this in a packet. First, we have an IPv6 header. IPv6 header obviously has a source address and a destination address. The source address is going to stay constant. After that, we have a segment routing header, and this segment routing header is nothing new. This was developed by RFC 2460 20 years ago. We are using the same constructs which were built at that time. We are just using them a little differently. Here, we are going to encode a network instruction, which is really a network program on how the packet should traverse the network from point A to point B. It's a sequence of instructions on tell what to do next. So, for example, in this particular case, you have a next segment with a locator, which takes you to that particular node, and you have a function on what to do on that particular node. We copy that information into the destination address field of the outer IPv6 header. Once that information is there, then the packet just traverses the network using normal IPv6 routing. And as a packet moves through the network, it just reads that instructions and start copying the information into the destination address, and that's how the packet moves through the network. So let's visualize it. By the way, before I get there, the last part of it is the IPv6 payload, which could be TCP, UDP, or anything else. Now, at a high level, let's illustrate how this network program and these instructions are executed through the program. So you have a destination address, which is located with the location 1 and function 1, which means on a node 1, once the packet receives where this location 1, function 1 belongs, the node 1 says, aha, this is something which I know, and I can execute that function. And that function could be anything. Then the packet moves forward. We copy the next location 2, function 2 into the destination address, and the packet just goes through the IPv6 network. It reaches the node 2, and node 2 recognizes it and then executes the function. Similarly, for the locator 3 and function 3. One of the key points to underline over here is that the only nodes, node 1, node 2, or node 3, are the ones which needs to be upgraded. So it really helps with the migration and towards the segment routing. Any node between the node 1 and node 2 doesn't need to be upgraded. It is just doing an IPv6 routing in the network. One of the things which I forgot to mention actually is, if you think about it, we are now encoding the instructions to go through the network. So we are really encoding, we are treating the entire network as a big computer. We are executing a network program to walk through the network using these instructions. If you code in C, C++, Python, or any other language which you like, you want to execute these functions which I talked about, but you also want to pass some of the global arguments between these functions. And that global argument is the metadata TLV. We put that metadata TLV in the SRH header, and that information can be shared across the multiple nodes through the network. So let's say you have an NFV node, which is encoding this information of network 1, locator 1, function 1. And these nodes really need to have maybe a performance information, some crypto information, or some other authentication information which needs to be shared across these appliances. You can encode that information in the metadata TLV. This is the paradigm which is mentioned in one of the NSH documents, and this is, I think, is we also try to incorporate into the SRH and try to encode that information in the packet header itself. The other thing which we have done is a tag field. So if you want to classify a packet based on a group-based policy, where you want to give access to a certain appliances for maybe HR system, some appliances for other normal company users, you can encode that information using this tag in the packet header itself. And once the packet reaches a particular node, that node knows what to do or which policy to apply based on this tag information. Now to summarize, what I have talked so far is, if you look at the top, we have a tag, which is in that on the right side on the SRH header. We also have a segment left, which tells us in which part of that network program, which instruction I am following. We also have the metadata, which I talked about, that if you want to exchange some information with the different NFV nodes in the network, you can do that. And this is, on the right side, is a picture which we proposed in IETF. It's all standardized. So there is nothing new here. We have done this. It's a draft which is out there in the IETF. So at this time of the talk, you might be wondering, this is all good, but what about performance? How does this perform? We did the first implementation of segment routing v6 about 3 years ago. We have learned a lot. We have optimized the upper part of the header for the hardware processing. That part of the header is used for underlay, for tenant, for NFV, for the VPN use cases, where you are encoding the information with segment left, you're encoding the information in the network program with the network instructions. The lower part of the header and the entire header is optimized for the NFV, for the container use cases, for software use cases. We have already done 3 hardware implementation inside Cisco. We have done the 2 open source implementation with VPP, FDIO, and with Linux kernel. And we have also done an interoperability with the other vendor, Barefoot, and it's been posted outside. We have funded the SRv6 implementation in the Linux kernel, and that implementation is also done and is available. And more of that implementation will be available in new versions of Linux kernel. So with Barefoot, we have also done the 6th overall implementation and 4th hardware implementation to prove that we have been able to do and optimize for the hardware processing everything about segment routing v6. We started on this journey of segment routing v6 in early 2017. Where we shared the idea, we published the drafts in IETF. Since then, we have multiple lead operators who joined us, as you can see in this list. We also have university and academia, which we have partnered with them to try to do this implementation. And this particular document is the first and one of the most important document you would read about segment routing. We call it network programming, and there are a lot of different functions, which I'll be talking on some of them today, are covered in this particular document. We have also worked with Professor Salzano and his team who have done the Linux implementation of segment routing v6, and it's available. We have also, as our commitment to the lead operators, we have also issued multiple drafts. On the left side, on the top, you will see the document which I have published about BGP SRv6 VPN. The bottom one is the ISIS draft. It's very easy to read. It's very simple. Please go through these documents and let us know if you have anything which we can discuss further. One of the latest document which we have published is the applicability of segment routing for the mobile network. We have done this with Satoru from SoftBank, and we have published this document only recently in June in IETF. This is the 5th document for segment routing v6 to our commitment to standardize everything which we are developing internally, and we are trying to share that knowledge with the large community and build a multi-vendor consensus. So far, what we have explained is what we have developed in segment routing in the last 4 or 5 years. We went over segment routing as a first introduction. We tried to explain why it is needed, and we tried to explain the applicability of it. What we will do is we will cover some of the network programming constructs in the rest of the slides, and then we will finish it off with the use cases, which is one of the most important things. In order to walk you through with ease with some of these use cases, we tried to build some convention. And that convention will make it easy to explain. It will make it intuitive and more human readable. Please do not think that there is any constraints in the architecture. The architecture is completely flexible, but for the ease of explaining it to everybody, we are trying to take. So in this particular case, we have a node K, which advertises a prefix AK. So you have a SID block, which is allocated, which is A1::64. From this SID block, this particular node can allocate the SID. This SID block is in the underlay, has been advertised to the other node, and it will try to be a normal IPv6 routing to reach to this particular node. So the first simple function which we have is endpoint. In the endpoint, you have a node which is A1::0. This is the most basic function in segment routing v6, where first go to that destination address A1::0 and then execute a function where you copy the next segment from the program instruction to the destination address. It's as simple as that. And we call it an end function, and that's why I'm just allocating a value 0 to it. So in this particular example, go to node A1 and then execute the instruction 00. In the next example, you have another node A5. You go to that node A5 just using the normal IPv6 routing and then execute a function, end function 00 on it, which is just nothing but copying the next segment in the instruction to the destination address. Now let's put it together. If we have a segment routing header which has A1::0 and A5::0, it means go to node A1. The A1 will be like, oh, I have to execute end function. The end function will be like just copying the A5:00 into the destination address. The packet then goes over the normal IPv6 routing to the node A5, and once it reaches A5, it again executes the end function. If there is no other segments left, it just pops the SRH and then sends a packet, the other IP packet to the node 1. Let me introduce a new construct, which is endpoint with then cross-connect to a particular neighbor. In this particular case, we call it end.x. Here we have go to a node. If you look at the SID block here, the SID block is A1::C2. So go to a node A1, and then the A1 recognizes that it's actually a function which is locally configured. That function will be C2, which means cross-connect to the neighbor 2. instead of taking a shortest path, it will actually cross-connect to it. So there is no IP routing happening anymore. It's just cross-connecting from 1 to 2. Similarly, if you have A5 colon colon C7, which means route to A5, which is just the underlay and normal IPv6 routing, and then you will cross-connect to the neighbor C7. So from 5, it will just cross-connect to 7. Putting this all together, here you have A1 colon colon 0 and A5 colon colon 7. So this is the network instruction. We go to node A1 colon colon 0, just a normal IPv6 routing. Then we steer the packet towards A5 colon colon C7 because that address has been copied over to the destination address. And once it reaches A5, it realizes it's a local function and it just does a cross connect from 5 to 7. If you see here, what we have done, the simplicity of this is that we have actually crossed 3 domains, DC, WAN, and did egress peer engineering with 2 segments. There's nothing complicated here. And all of this is automated using either a distributed controller or distributed approach or a centralized controller. This is the same use case which has been showcased by Google and Facebook with the Edge Fabric at SIGCOMM and with the Espresso use case which they have. TILFA this is our first use case, the TILFA, or we call it a topology independent LFA. In this particular case, we have been shipping this technology for about 3 years. It has been very widely deployed. We are able to do sub-millisecond convergence with TILFA. It's easy to understand. The IGP does the post-convergence path calculation, and it's fully automated. It's predictable because it's a post-convergence path, and it can be deployed incrementally. So one of the key benefits of it is that whatever we have been able to do with SRMPLS, we can do the same thing without much change with SRv6. So in this particular case, you have a node 6, and node 6 has an instruction to send the packet over to 5, which is normal IPv6 routing. And at 5 will just do an end function, which I described earlier. At 6, it will also calculate using IGP fully automatically. It will calculate the backup path, which will insert a new A2C colon colon C4 segment in the list. So the link between 6 and 5 fails. The packet comes to 6. 6 immediately discovers that. It inserts a A2 colon colon C4. And the packet just traverses through the network using normal IPv6 routing to node 2. At node 2, it says, aha, it's an n.x function, so it will just cross-connect from 2 to 4. It will not try to do routing because that will cause the loop, so it just cross-connects from 2 to 4. Once the packet reaches 4, it will send the packet down to 5 because the link between 2 and 4 has a larger matrix. One of the main point about this is that this particular solution is completely topology independent. It can be built incrementally, and we use SR policy on the node 6 to encode the information. It's about it's just encoding and inserting a new segment in the SRH header, and we are able to achieve the sub-millisecond convergence with TILFA. Let's talk about our next use case, which is how do we do overlay with SRv6? You will see it will be intuitive, it's simple, there is nothing complicated here. Let's imagine you have 2 tenants, tenant green, which is connected from 1 to 3 and from 2 to 4. So BGP, you can use any overlay protocol, whether it's BGP, Lisp, SDN controller, it doesn't really matter. But for the simplicity, I'm just showing the BGP use case here. So BGP signals the information from 2 to 1, and it will signal for the prefix v64 with the next hop as A2 colon colon C4. Once the route reaches the node 1, and the packet comes down from node 3 to node 1. The node 1 will encapsulate with the outer IP header and put the A2C4 in the destination address. And that's it. Now you're just routing normally to the node 2. Once the packet reaches node 2, node 2 will be like, oh, this is again n.x, so it will just cross connect from 2 to 4. It's that simple. See, in this particular case, we only had a need for one segment ID. We didn't have to put any SRH, so we didn't actually put any SRH into the packet. We can achieve the same functionality with one ID, so we just encapped an inner IP address with an IP packet with the outer IP packet. In this particular case, what we have showcased that we have eliminated the need for UDP, we have eliminated the need for any other encapsulation protocols like VXLAN or GRE, and try to achieve the same thing with the simplicity of segment routing v6. Let's try to touch on another use case, which is overlay with underlay SLA. So in this particular case, now you have an SLA where a route needs to be reached, a green tenant needs to be reached with a low latency. So what do we do? In this case, if you follow the segment routing, this is nothing different than a TE solution, an ODN solution, which we have shipped with SRMPLS. We advertise the BGP route with the SLA. And when the route comes to me and the packet comes to the node 1, the node 1 knows how to encapsulate that data into a particular SRH header. So let me showcase that. Once the packet arrives a particular tenant over here, node 1 will now put an SRH header, and that SRH header is the segments of it is fully automated through a controller or through distributed approach. And the segments are A2::C4, which is the segment which is sent through BGP from node 2 to node 1, and A3::0, which is the intermediate segment which has been pre-computed to take the low latency path from node 1 to node 2. So in this particular case, node 1 does a simple function where it copies over A3::0, which is the first segment, into the destination address and sends the packet over to the network. The network just takes the packet to the node 3. Node 3 looks at the next instructions, and that based on the segment left, and it copies over that information over to the destination address again and sends the packet down. Once the packet reaches A2, again, A2 will just recognize that this network segment belongs to me, which C4 is a function where C4 means cross connect from 2 to 4. In this particular case, what we have done is we have not only eliminated the need for any encapsulations, we have not only eliminated VXLAN, GRE, and a bunch of other convolutions. What we have done is we have solved a problem which these protocols cannot also solve, which is the traffic engineering. And we have been I'm showcasing right now an example for IPv6, but this will work seamlessly for IPv4 as well, or even for the global internet cases. In this example, I'm going to show, this is another use case with the integrated with NFV. The same green tenant, we have two green tenants, which is server 3, where app 32 is in a container. You have another tenant, green tenant, where the app 76 is in a VM. And on top of it, there is an SLA requirement for the packet to be steered with the low latency from the node 1 to node 4. And again, you will see it's very simple. It's the same constructs which I have showcased so far. The packet comes to 1. 1 has pre-computed a path using, again, a centralized or distributed approach and inserted into the 1, which is really mapping to an SR policy. So when the packet comes to 1 and we steer the packet into a particular SR policy, that SR policy will do a behavior to encap the packet with SRH and an outer IPv6 address and copy over the first segment in the network program instructions to the destination address. Packet goes to node 3 based on A3::A32. Once it reaches that particular node, it's an app. We the app we will send, the node 3 will send the packet over to the app. App does, like for example, if it's a firewall, it does its job. Packet comes back to node 3, and we will re-encapsulate the packet, copying over the next segment, A4::0 into the instruction. If you see in this particular example, what we have done is we have the node 3 has no state information on where the packet has to go. There is no state maintained at all. Versus in NSH, we kind of try to maintain that state. So this solution makes it more scalable, it makes it more flexible, and if any of these servers or apps goes down, controller knows how to recalculate it, or you can calculate it distributedly. So there is no flow which is maintained. Also, the application can be segment routing aware or may not be segment routing aware. We have built proxy functions, which you will see in that network programming document, that these proxy functions will take care of it seamlessly. And the app can be IPv4, IPv6, or even Ethernet. And the inner payload can be any of that. Now, once the node 3 has done its thing, node 3 will copy over A4::0 into the destination address. This particular node is pre-computed again for the low latency path, and the packet is sent over the IPv6 network. Once the packet reaches the node 4, the node 4 will does its normal function, which is end function, and then copy over the next destination address, which is A5::A76 into the destination address. And once this is done, the packet is again shipped out to the node 5. Node 5, once it receives the particular packet, it knows that it's again an app which is running in a particular VM. It can be a proxy, or it can be SR aware. Node 5 will then strip off the outer headers, send the inner header to the payload to the app. App can be IDS or firewall or any other app. App returns the packet comes in, we re-encapsulate the packet into the SRH header, does a normal processing, and copies over A2, which is the next instruction, A2::C4 into the destination address. And we push it on the interface. The packet traverses from node 5 to node 2 with just normal IPv6 routing. Once it reaches node 2, that slide is missing. Once it reaches node 2, we strip off, we call it a PSP behavior, but we strip off the entire outer IPv6 and SRH header and sends the plain IPv6 address to 2 to 4. In this particular example, again, as you have seen, we have showcased multiple aspects. We are trying to showcase that we have integrated with overlay, which could be any control plane. We have included the NFV apps into the SRH header itself, so it becomes an intermediate hops in the network instruction. We have also included the SLA requirements which the app may have, all of that into the same SRH header. And we have been able to achieve all of that without any other encapsulation which might be required. As I said earlier, we have partnered with FTIO. We have developed these functions which I've showcased so far, including the proxy functions for the NFV, into the FTIO project, and this code is, we are committed to not only do it for VPP use cases, but we are also doing it for the Linux kernel. So this code I encourage you to go to segmentrouting.net and all this. There's a tab for the open source code, so you can go and review that. So, Spray is another use case for segment routing v6. This is a use case which Comcast is doing in field trials right now, and this is what they are deploying in their network. So with the Spray use case, one of the things which they are trying to achieve is to have a multicast-free core. Multicast has been deployed in the core for very good reasons, but we believe there is another way where we can reduce the overall complexity for the multicast using this particular use case. So what happens here? A content provider It could be VPP, it could be any node which understands that. You're peering to a content provider. The content provider will replicate the information to the CMTS, which will then do the multicast function. But in the core, it will just be a unicast. So it has a network instruction, which is a spray policy on top. The spray policy is B2 colon colon and B4 colon colon, which means take my packet from VPP, which is the edge node, unicast over to node 2, and then to the CMTS. Once it reaches a particular CMTS, then the packet can be multicast to the gateways to provide to a particular channel which customer is subscribed to. Similarly, we have another policy which will take you to a different geolocation, and this is again very simple pre-computed policies which can be automatically computed. You are unicasting from the VPP node again to B3 colon colon to B5 colon colon, and once the packet reaches B5 colon colon to a particular CMTS5, you just multicast or unicast the packet after that. So you see, in this particular case, we have been able to do SLA because you can have these policies which are dependent on some SLAs. We have also got rid of the multicast in the core, and we have been able to do a flexible approach because if the topology changes and controller is in the picture, it can recompute the path. And one of the key points to highlight again here, just to emphasize what I have said earlier, is that not the entire network needs to be SRv6 aware. Only the nodes which are useful or are needed needs to be SRv6 aware. So we have been able to only do this with only 3 or 4 nodes which are upgraded to be SRv6. Rest of the network just continue to be a legacy IPv6 network. This is one of the newest use case which we have built. We talked about it recently. I'm going to switch a gear a little bit, and instead of talking about SRv6, I'm going to cover this use case with SRMPLS, but please in no way think that this cannot be done with SRv6. In fact, it's as intuitive as it can be done with SRMPLS. So in this case, on the right side, you have a service provider network which has presence all over Europe. You have a node 1, which is Lisbon. You have a node 7, which is Athens. So in this particular case, we have a label stack using SRMPLS, which has been pre-computed, and that one of the label stack is 16007, which is default routing. The BGP best effort, just taking the packet from one point to another point, and that's the LSP label. You have another label stack, which is providing you the bandwidth guarantee. Now, this label stack is actually tying to an SR policy on node 1, and that tying to SR policy is mapped to a particular another label. We call it a SID or an identifier. You can call it a binding SID. And here the binding SID is 24002. We have another SR policy where somebody wants to go from node 1 to node 7, but wants to take a low latency path. So it can go from node 8 to node 9 to node 7. And that label stack is 16009 and 16007. Again, this is only on node 1. It's an SR policy mapping to a low latency, and it's mapping to a particular identifier. We call it a binding SID. Now let's look at how this helps. We have, with that service provider, now let's say we put 2 more blocks in the picture. We have on the left side an enterprise network E1. We have on the right side another enterprise with the same site, with a different site 2. And app 1 wants to just do normal default routing. So what it does is the E1 encrypts the packet which is coming in, and it encapsulates with the outer packet and sends the packet to the service provider node 1. Once the node receives it, it will just do the best path routing using the LSP label, and the node reaches node 7. In this particular case, the appliance or application did not have any any traffic engineering requirements, so we did not do anything different. We just use the normal MPLS routing, MPLS label switching to take the packet from node 1 to node 7. Let's talk about a different application. In this particular case, you have an application, it's a normal world use case, where the application wants to guarantee a 10 Mbps bandwidth to be available from node 1 to node 7. In this particular case, E1, which is the enterprise network, recognizes that because it's in the best position for that particular node in the enterprise to be able to realize what the app needs. Once it realizes that, it pushes a label 24002, which was that binding SID or an identifier, which I mentioned earlier, and ships the packet over to node 1. Once the packet reaches node 1 realizes that, oh, this packet came with 24002. We steer the packet into an SR policy. The SR policy derives that label stack, which was to take the packet from 10 to 11 to 12. And this is done, again, automatically, even if there is something which changes in the topology of the service provider network. It can pre-compute the path, but the binding SID or the identifier does not change. It continues to remain the same. So now in this particular case, we have been able to do for app 2 a bandwidth guarantee from node 1 to node 7, and the packet goes to node 7, and then we take out the outer LSP and sends the packet over to E2. Similarly, you have another app which needs low latency. In this particular case, we have been able to just push another header, another 24003 label. Once the packet reaches node 1, we steer the packet into a particular SR policy, which is only on node 1, and then that has a pre-computed path, and that path is node 8 to node 9, and finally to node 7, and eventually to E2. So you see, in this case, we have been able to steer the packets over the SP network, but on top of it, we have been able to realize the SLA requirements for the applications. To summarize, the binding SID, which I was mentioning earlier, is completely crucial for the enterprise. It's secured. I have not tried to explain that over here, but if you're interested, please come to me and I can explain some more in a more technical depth. We also have a counter per binding SID. That counter computes, which allows for the usage-based billing. We also have the delegation of the application recognition, the policy decisions. We leave it to the enterprise. We do not want to create that paradigm. And who knows it better that when an application needs a non-default path, and which non-default path is needed based on the application needs, it can just attach those right labels and send it forward. Binding SID has other applicability. We can even stitch together with the NFV applications and other parameters. One of the key points to mention over here is the edge devices in the normal SD-WAN scenario are the ones using some SD-WAN controller and probing the network, but that probing still goes over some default path. Using this binding SID in the SD-WAN controller, you can actually the SD-WAN controller can actually check the applicability of a path in a particular location of a network. So it's more granular, and it also opens up more services where it can make better decisions. For instance, if you're steering into a non-default path and you have an SD-WAN controller which is using a binding SID for high bandwidth, but it's also using no binding SID for the normal default path. If the normal default path is as good as that path which you're using for the high bandwidth, you can switch over the traffic now to the default path because it's less expensive. So you see, now you have more ability to be able to make these decisions based on much more finer requirements. We also have for the SP, this also enables cases where the service provider can actually now do monitoring in their own network for their own use based on the low latency and loss so that they can tune their network better. And it opens up the possibility for the richness the service providers have in their network to offer new services. So if there are enterprises which are serving the applications which are very time critical, we should be able to do that. All right, so I'll quickly run into this, into the significance of segment routing into the mobile network, but there is a lot more details which we have mentioned in the draft, so please feel free to look into that as well. And if you have specific requirements, you can talk to me. But in this particular case, this is a classical mobile network. It's completely fragmented. You have a RAN network, you have EPC, and you have an SGI network with the N2 anchor point and L3 anchor point. And we are doing the GTPU tunnel encapsulation. It's a non-optimal path. There is no SLA requirements which are there, so we cannot achieve any SLA using this network. However, with segment routing and 5G, you can do it by using some of these functions which have been described in network programming. And some of the functions that you might know, like for example, end function for the L2 anchor node would mean that once the packet comes to that particular L2 anchor node, it just needs to send it to the next node. Or n.b6, we call it a binding SID, which means that if the L2 anchor node is using the classical routing on this side and IPv6 on the other side, we can actually create a policy which is end.b6, and you can steer based on an SLA requirements into that, into the uplink or downlink from the L2 anchor node. Now with that, there are, of course, more use cases, service pipelining, microservices, load balancing. If I have more time, we can go over that. But as I said, if you have any questions or applicability of this, please come talk to me, and we can partner and try to explain more technically these things. So in the end, I think what we have described is the segment routing v6. We started with what is segment routing. We tried to explain the applicability and the need for IPv6 network and a need for applications to have the SLA requirements. And we tried to explain the simplicity of segment routing v6 and try to eliminate some of the protocols which have been developed over time, and in the end covered it with some of the use cases. So with that, I open up for any questions if you have.
Hello, John O'Brien from the University of Pennsylvania. Thank you for this talk. I appreciate that you found an opportunity to use the phrase legacy IPv6 unironically. And I was wondering if you could comment on some challenges of using SRv6 in an interdomain scenario in light of some of the challenges we've heard about recently.
So we have deployed SR MPLS in the interdomain scenario using distributed or centralized approach, and it works seamlessly. We have created these concepts of like binding SID, which I was described, which is acting as the bridge between one domain and another domain. So you send the packet using that binding SID, and now the next domain knows what to do with it till it reaches the other side, and then there is another binding SID which maps it to the next domain. And it will work the same way for segment routing v6.
I guess my concern is that the dependency on extension headers is going to limit the adoption in the same way that we're seeing challenges with extension headers in other ways.
So we have already seen some of the adoptions with the extension headers in some of the other service providers. The limitation, yeah, I'm not so sure about like specifically which particular limitation, but we can talk more and see the specific limitation you're referring to.
Austin Brower with Fairpoint Communications. I'm over here.
Hi.
To your right. To your right. Hi. Back on the slide where you described the use case for integrated NFV, could you describe how the SRH information is maintained when you're passing an SRH application that's unaware of the SRH header?
Sure. I'll just go to that slide. So we have created, hopefully this will be quick. Give me 1 second. Yeah, in this case, let's assume that 5 is the application 76, which is running in a VM, is not SR aware. We have created a function called proxy functions. Those proxy functions will, there can be multiple. There can be an explicit proxy function or a dynamic proxy function. The dynamic proxy function will cache the information once the packet comes from 4 to 5. It caches the SRH and the outer IPv6 header. It strips that header, saves it in a cache, sends the bare minimum packet to the app. Once the app does its processing, the packet comes back. There is a policy which is applied on that particular interface, and that will re-encapsulate the packet and send it forward. There are different flavors of it. We call it, and it's listed in in the network programming draft, but it's end AM or end AS or end ASM. There are different flavors of it which we have created, so it'll work seamlessly. But we are also building some apps which are going to be SRv6 aware.
Srinivas with United Private Networks. A couple of questions actually. So for a service provider, why should they choose SRv6 or SRMPLS? What should be the criteria from a core perspective?
You don't have to, but it's really
multiple options.
No, I mean no. It's really depends on if you're running out of the address space, and if you're moving towards an IPv6 network, how do you extract more out of it? How do you extract more value with all these different use cases and be able to provide more services to your customers who are really in need for the traffic engineering? Because we have heard that the customers sitting on the edge of it can also discover that there is something wrong in the network, but there is no way for them to go to the service provider and say, hey, service provider, we'll give you more money, can you offer these services on top of it, right? So it does enable those applications.
And the second one, on one of the slides you showed, you have reserved a bandwidth of 10 meg.
Yeah.
What mechanism did you use to reserve bandwidth?
So we have, within the SP core, we have a lot of computation which is being done and signaled all that information to the controller. So it's all dynamic. So if the bandwidth actually changes, then the controller can recompute the path to a different part of the network.
Right. But have you actually reserved 10 meg on
There is no
band?
reservation.
There's no reservation.
It's basically based on how the traffic is flowing. We
the current
get that,
situation.
yeah, we get the information, we send it to the controller. Again, we are not maintaining any state in the service provider at all.
Okay, thank you.
Yeah.
Steve Ulrich, 2 questions. One, how do you ensure a truly loop-free topology in TILFA if not all nodes are capable of processing the extension headers?
The nodes which are not capable, again, this is computed by the controller and or the IGP locally. So we can, if the nodes are not SRv6 aware, it's just going to forward it to that particular node just using IPv6, basic IPv6 routing. And we have mechanisms where if you're using the SRH and we decrement the segment routing, segment left counter, if that changes to 0, then and it comes back, then it's a loop, and then we detect that.
And second question is, how is the spray use case different from AMT other than explicit path selection?
I'm not so sure about AMT, so maybe we can talk offline and discuss that. Oh, the ingress application. So in the ingress application, in the core itself, you're not doing any kind of So in the core, you're not doing any kind of multicast. You're just sending the packet over to the edge, which is doing the replication for you. In the ingress, on the ingress itself, you're going to just do the replication and send it forward. Any other questions? Let me go to that case. Go ahead.
Just in benefit of everybody to hear me, the spray effectively do the ingress replication on a small scale because it's replicating the data carried over the core, right? Mm-hmm. It's a unicast replication.
All the way to the CMTS, yes.
All the way to the CMTS.
Correct.
So the bandwidth is consumed n times.
Okay.
It could be good enough, just making that point. I have other question to the NFV and the proxy action, just to confirm that the corner case is that we will have to keep the per flow states in the proxy, because the packet from the same destination to the same source may requires different service path. So what is the worst case granularity of the proxy?
Let me come talk to you about that.
Okay.
Yeah, I'll come right now. I'm out of time. But yeah, there is a way we don't have to maintain those states. All right. Thank you, everyone.